Good evening. Welcome. Can you please stand as we welcome the procession into the venue? Thank you. You may be seated. Thank you.
It is my pleasure to welcome you all. In particular, I would like to welcome our Deputy Vice Chancellor for Research, Innovation and Postgraduate Studies, Professor Sibusiso Moyo. Thank you very much for being here. We know how busy your schedule is. We appreciate it. A special word of welcome to our honorary speaker, Professor Stephen Matope, and his wife, Dr. Jasmine Matope, and his children who are here in present. Then we also want to welcome our colleagues, specifically from obviously the faculty and the Department of Industrial Engineering. And then also all the friends, collaborators, and students, and everyone else attending in person and online. So thank you very much for making time for this. Professor Stephen Matope, we're really privileged and proud to have this versatile academic in our ranks. He ticks all the boxes of an academic. His research centers on the processes and systems that are used in advanced manufacturing. In terms of research, he's published a lot of papers, more than 105 peer-reviewed journal articles and conference papers, and he supervised a large number of students, including 10 PhD students and over 70 master's and bachelor's student projects. He's also a registered professional engineer who's carried out over 60 industry-based engineering projects in South Africa manufacturing companies. And he's a member of quite a long list, I won't name them all, of professional organizations in industrial engineering, both locally and internationally, and also in engineering education. Speaking of education, already as a PhD student, it was recognized that he's got a knack for teaching. He was recognized for his teaching talents, and since then, now as an academic, he served engineering education in Broad, amongst others as the first coordinator of the European Network of Innovative Learning Factories in South Africa. He's also helped to organize and host quite a number of international conferences, more than most academics, I would say. Not only for the Network of Innovative Learning Factories, but also for the South African Institute of Industrial Engineering, and triannually international conference on competitive manufacturing that he's been doing since 2016. So those are a lot of conferences, and those of you who have been involved in conference organizing would understand the commitment that implies. So thank you for that. He also serves as external examiner for 4 South African and 2 Zimbabwean universities. So he's making a significant contribution to teaching and learning also in the engineering space. Recently, Professor Matope initiated a collaboration between Chemnitz University of Technology in Germany and our Faculty of Engineering to facilitate staff and student exchanges, joint research, and joint funding applications. He's also a collaborator of the German-based Fraunhofer Institute, which is the world's leading applied research organization. So I'm going to hand over to Professor Matope to tell us himself more about his research. Thank you very much, Stephen.
Well, first and foremost, thank you very much. I was not expecting such a big crowd, especially during this break. Every one of us was supposed to be on vacation, on leave for about a week. But thank you very much for sacrificing your break. I am very, very much thankful. And thank you, Professor Thulion, for the wonderful introduction. Thank you. Well, I need to say thank you to the rectorate, Professor Sibusumo is here, the deanery. I'm happy you've given me opportunity to come and present my little work here. Then also the Faculty of Engineering, I know from different departments you are here, thank you very much. Industrial Engineering Department, thank you very much. The chairman, previous chairman, current chairman, thank you very much. To my promoter, please allow me, Professor Andre van der Mede, who took me as his first PhD, I think first PhD black student. Thank you very much, Prof, for believing me. Here I am now, because of you. Thank you very much. And also to my colleagues, I'm seeing several lecturers here. Thank you very much for your presence here. And to my students, I'm happy that some students here, my PhD students seated out there, thank you very much for the great support. And I would like to say thank you to some students in absence here, my PhD students. We've worked quite a lot on this additive manufacturing. So my dear students, Dr. Mugwago, I think is online. And also Dr. Mbunzi, she's also online. We're working together with them on this wonderful project. So I've tried by all means to share what we're doing with these PhD students of ours, what engineering fields we have managed to accomplish. And in my presentation, you're going to see most of their work in there. And I hope that through this lecture, my dear students, your work is going to be published or to be made aware worldwide. And I hope your Scopus index is also going to rise up, and also your Google index because of this presentation, because they're also going to see that I've quoted you. I've also put you in my references. To my blessed family, I need to say, my wife, thank you for the help you've given me. And for my wife, well, normally with my PhD students, I would simply just say that that's my wife. They also say, Dr. Jasmine Matope, with a PhD here, as a way of motivating my students to say, if the wife could get a PhD at Stellenbosch University, so can I. So I'm happy that all the PhD students who have come through my hands, they've managed to get a PhD qualification from this institution. I'm very happy, honey. Keep it up. Right, and also to my daughter there, thank you for the support, and also my son, thank you very much. The collaborators, you've already mentioned by Prof, thank you. Yes, the German Institute of, well, we say the CSIR up there in Germany, but it's more than that. They are into re-engineering. So I'm happy to have worked with them, and also the work I'm doing here, we're collaborating with them. Cambridge University as well, we're also collaborating with them. I really acknowledge their support. Then also the Almighty God who gave me such a family. Colleagues, deans who understand, yeah? Vice chancellors who would understand. I really thank God for giving such a wonderful community. Well, my aim here, I'm just looking at additive manufacturing, a game changer in advanced manufacturing engineering. Game changer in the sense that there are things which we can't do, well, normally or traditionally by machining, but with additive manufacturing, we are able to produce those complicated geometries of engineering products. So we can simply say, I need to say this, I think all of us are quite familiar with printing. You type your text, okay, in Word, whatever, then after that you connect your computer to your printer, then you print. That's exactly what we are doing in additive manufacturing. But now we will be printing layer by layer powder, building it up, or even some laminar paper, building that up using a binder. So that's exactly what we are doing. So it's a virtual 3D version of our final product. Then we simply print it out layer by layer, building it up into the final product which we want. Now, so my aim here of my presentation here was simply say to show that really this additive manufacturing is a game changer, especially in producing components of cars using hot stamping forming tools. Right, there are several benefits here. We can say fast product production or prototyping, benefits of additive manufacturing, reduction in lead time, as I can see in my presentation as well, and also reduction in manufacturing costs in some cases, and also increased product customization. That which you couldn't do using conventional means, now we can do it easily now. Then also the quality of our product can also be improved. And also, as I said earlier on, intricate and complex geometries of engineering products which you want to make, they're easier to make using 3D or additive manufacturing. So, as an engineer and myself, I'm quite practical. At times I don't want to work with things which are up there. So I try by all means to apply my engineering to real things which are working, which are tangible. No wonder why Prof. also said that I've supervised over 60 command-based projects with my students. So in this case here, we're looking at hot stamping process. The hot stamping process, we start first of all, in our case here, with our blank, which is made of tool steel. Then we austenize it. We are heating it to a temperature, since it's steel, the temperature above 800 degrees Celsius to 900 degrees Celsius. Then after heating it to that, that's where the hot comes into play, why we call it hot stamping. Then we pick it using a robot or what it means, then we put it into our forming and quenching press here. That's where most of our engineering work has been evolving on, or revolving on with my PhD students in additive manufacturing. Then when this is done, we then can open our press, then we have our final product out. So here, well, we are much concerned about doing this faster and also achieving our mechanical properties of our final product. Now, the case we are looking at here, we have got an object, a rocker panel. That's the one which we manufactured using this additive manufacturing, additively manufactured tool. So that rocker panel, normally it's between the sides here, in the rear and the front. So it's a reinforcer here. So that's the panel we are producing. And this panel, we got it, we can say, well, we can say this product, we actually got it from our Farnova colleagues. And they wanted us to improve the production of it, to produce faster. Because the demand for it, more cars, got more cars, of 100,000 of demand for this product. Good, then our purpose statement now, making it specific now to this rocker panel. The dimensions here is we are saying, we're talking of 745 millimeters times 174, so it's this big size. So it's a tool like that, a punching tool, which we are using to produce the final product, which is here, right? Now to produce this, we do have our tool, which happens to be like that, having the negative form of our final product. Now that too, since we are doing hot working, we need to cool it. So currently, or may I say during that time, before the research, in Germany, Chemist University and Fraunhofer, they were using straight channels for cooling because that was the only way they managed to come up with. So it's to come up with the final products. But as you can see, those channels, there are a lot, you can say, spaced and also few, and also produced by drilling. That I can limit the length you can drill, and also how close to the surface you can go. Okay, so we find that with this kind of arrangement, we're actually having longer cooling times, which would consist about 30% of our steeping cycle time. Then also would also result in thermal stresses because the drill channels could not absorb the heat SUV uniformly, right? And that would also again result in some compromises to our tool life, okay, when it comes to the final product or the hardness of our product. So you find that the product would have uneven hardness, such that when it comes to performance, it wasn't performing as should be. So again, we are also saying that since heat is not absorbed easily, we are also saying those high temperatures will also result in high wear of our final product, of our tube, of our punch. So these were the problems. So we need to find a solution here. Now, let me tell you a bit about the blank, which was used by our colleagues in Germany, and we were working on. It's actually ultra-high strength steel, designed for hot forming processes, and that high-strength steel is quite good for reinforcing our body parts of our cars. So those are the mechanical properties of our blank. So with this now, since you have seen our problem statement, so our specific objective in this case here is to make sure that we come with a stamping tool which can take it out of our product, 27 degrees per second, and also doing that from a high temperature of 800 degrees Celsius to a temperature below 200 degrees Celsius, because that's when we have the magnetic structure now, which is quite hard, which is quite hard, which can resist a lot of scratching and can also resist a lot of wear. Then with that, that being our objective, we then find ways now as to how we can remove this heat fast in making our final product so that we can produce a high-strength material. We need to maximize our cooling rate. So the maximization of our cooling rate, we would really like to improve the cooling system parameters within our forming tube, and also making sure that the mass flow rate of our coolant is also high. So that is defined by our tube, which we are making. As for the coolant temperature, the entrance cooling temperature, it was 20 degrees Celsius. Let us continue here. Now the method we used to come up with this final tube, first of all, develop the mathematical models. We did transfer those big equations. At times which would make some of us not do thermodynamics. So we really use those to come up with the right parameters there for our channels. And then we also had application models on a benchmark. Then after the evaluation using simulation, in this case, pump stamp was used. Then we had to do the design and manufacture. That design and manufacture was done here locally using our equipment we are having in our STL lab. Then we did experimentation as to find out whether the cooling rate was within acceptable means, and also the final temperatures were achieved, and also the hardness was also achieved. Then we did some evaluations there. Now, we do have, we had to find several possible layouts to make sure that we come up with our final, desired design of our cooling system. So we had 4. So we had to evaluate those according to quality and also GFM, or design for manufacture. How easy to manufacture it could have been, or it could be. Then also we had also to design the tool now, according to GFA, design for assembly. So we had that criteria. Then after that, we went to do our evaluations and identified the most suitable configuration, which then happened to be configuration number 2. Now with that, we also had to do some simulation just to see whether the desired temperatures are achieved. So we've got our straight cooling layout here. And the desired temperature is 200. So we say of the final there, it's the 200 there, it's reached almost after 8 seconds. But with the conformer, we see that with our simulation there, we found that it was reached almost after, may I say 5 seconds. So with that, after that simulation, then we went on now to the manufacturing. The simulation, why we do it, is that we don't want to risk producing a product without knowing that we're going to achieve what we want using the given parameters. So simulation helped us to come up with the right parameters before manufacturing. Right, when it comes to the hardness, also the straight cooling layout, we found that 400 to 500 was difficult to reach. Okay, somewhere around 10 seconds there. But with our conformal cooling, we found that it can be reached, say, after 5 or 4. So somewhere after 5 seconds, we can reach the Rockwell hardness number of 500. So having done that, we were then sure that we can start doing the building of our tool using additive manufacturing. So we then had our design as shown now here, but we need to say that in some cases, it would be very difficult to build it all because it's quite big. We're talking of, as I said, 740 length and the width. We're talking of 174. So it's quite big, and it will take a lot of time. So what we did then was that we had to do hybrid machining. I mean hybrid manufacturing. So the bottom part, we made sure that we had to do the machining itself, the drilling of the holes, especially these ones here. But the part where we wanted the cooling to be more, which was now near the surface, that's where we did the additive manufacturing, the 3D printing, so layer by layer, okay? Coming with those geometries. As you can see, it's no longer the straight, which you saw in the first case. Now they are following the profile, or defining the profile of our final product. So that being the case, it meant that the water channels now were closer to our product, so that it can quickly be removed. Right. Now, when you look now at the material now, which was used to come up with the tool, that powder was our H13 tool strip. So we had to lay that powder, then laser fuse it, put another layer, laser fuse it, put another layer, melt it by laser, building it like that. And the properties of the H13 tool steel are also displayed here. Now, the machine which we used, that's our M2 laser fusing machine. Right, with this tool, at one time, it was actually the best of the two in Africa. That's how our technology had really grown up to be, but unfortunately we're sorry that it's a bit down in some benches. But we are saying we're fortunate that whilst it was still in its useful time, we managed to use it, and those were the parameters we used: the laser, the layer thickness we used, 30 microns, and the hatching and the like. Now, we then, can I say, summarize everything now here? It's the manufacturing. So we did the machining of the base. Then out of that, we did the drilling of the holes through which the coolant is to flow through. Then after that, we then did the printing, layer by layer. But are you seeing that there is need of great precision? Because those holes, we still had to develop them in the 3D. So there was very great precision there, and I need to thank our technicians who helped us with that. And we had to build it, and then after that we had to do some stress relieving, some heat treatment using some facilities which are having around. Then after that we had to do the final machining just to make it polished up. Now with that, we then had to try it, to test it. That's now the experimentation now after the building. So we're saying we are doing the pressing at the same time, we're forming our part, and at the same time also removing what? It fast, at high rates, so that we can achieve the hardness required to produce, or to use it to produce a product in industry. And those were the properties of our blank. Our blank was 950 degrees Celsius. Okay, the transfer time from the furnace to the forming with press was 10 seconds. Then the forming speed, how we had to move it down, our punch moved down to come up with a final product. It was those 200 millimeters per second. Right, all goes down like that. So when it comes to pressing, we're using all hydraulic. But let's say for this, we did not do the testing here. We had, after manufacturing the tool, we then had to ship the whole tool to Germany. And they then had to test it. So since it was a collaboration. So our chemists and our front-over guys were helping us with that, and I'm also very much grateful. May I say, as you know, Prof. Dimitrov, he was really key in this. So I was working with him as a co-supervisor for the PhD students. I really learned quite a lot from him. Now, the diameters of the channels for the hot forming tool, where we do have that one for conformal cooling, we are having it 0.005 millimeters, but as for the conventional, at 0.1, 0.1. Right, I think those are the values we used. So after we did that, we then had to compare simulated results or findings with our final experimentation. So with that, we found that the experimentation results were really better off than our simulation. So we are saying in this case here, for the code, we're having there, I think, after sort of 7, that's where we were reaching the 200 mark required. But here in the conformal cooling, which had really produced the conformal cooled product or tool, we find that we are reaching that 200 degrees Celsius, somewhere down, well, somewhere, right, it's already below there. Okay, so that in 5 seconds, we are really way down. Actually, somewhere we're just before 4, you're already reaching the required temperature. See. So with that, we then had also to do some comparison, now making just having a closer look here. So for our conventional, the straight one, here we go. Okay, then for our conformal, here we go. So comparing this, time to reach the target temperature of 200 degrees or less. For conventional, we took 7. But for our conformer, which we come up with, we took 5. So 5, but note that at that 5 seconds cooling is not coming to 200 dead. It's actually way down. So performing quite better. So we're getting 167 degrees Celsius there. But for conventional, in 5 minutes, we're still up. So as far as we are concerned when it comes to manufacturing, time is money. The more we can produce per given time, the more the money. And in this case, we're talking of a reinforcer used in cars, and we see how many cars we are having all over. So in short, you are saying those really be replaced. Well, like there's, the life of a car sometimes simply 5 years. So you need to get more and more cars are replaced. So we are saying that with that faster production, we are really going to meet the demand of vehicles which require these reinforcers. Then when it comes to the average cooling, in 5 minutes, for our conformer, we're having it as 170.8 degrees Celsius. But with our conformer now, compared to the conventional conformer, I think that's 127.4 degrees Celsius, which makes it 9.6 degrees Celsius higher, which is better performance. But well, as far as the minimum requirement is concerned, okay, for 27 degrees per second is concerned, well, that is satisfied. Then we also checked again, as we stamp or press, getting these pass out, okay, what about the temperature deviation of our tube? We found that after pressing about 20 blanks, right, our conformer cooling stagnated now at 45 degrees Celsius. So that means you can even produce more, but still having the 45 degrees maintained. But when it comes to the conventional, the temperature really it was 70 degrees Celsius, which is quite high, which means there will be more thermal shocks on this tool. On the conformer is better, that means now less heat, that's less thermal stresses, and better performance of our tool, and also life. Now, when we look at the other requirement to do with hardness, for that orange, you see that the hardness there was quite high in all cases as compared to the conventional, the straight cooled. If we're looking at cooling time of what? Of 5. So we say we really managed to do better there. However, after having said all these things, okay, I need also to say one thing. Our colleagues in Germany said, can't you produce more of this? Then I had an awakening and said, does it mean that we are this good? That these guys up there are now saying, can we produce more of this? Right. Well, it really shows how, the level we've reached when it comes to additive manufacturing, especially applied to tooling. But let me also say that it's not all roses. There are also challenges with this additive manufacturing. Yeah, people say, let's go for additive manufacturing, but it's not always roses. There are issues there, especially to do with the residual stresses. Because by the way, you're melting your powder, add another layer, melting it, add another, right? So that there are thermal changes there which can really result in residual stresses, which can result in delamination. Your tool, the layers not really merging, not refusing together. Then also form different deviations, some distortions, instead of you coming up with the right thing, you find maybe swapped and the like. Also cracks because of these thermal stresses. And so also, well, fatigue again. But I'm happy that with one of my students as well, he worked on this research and looked at the influence of part thickness. So if we found that the higher the part thickness, the thicker the part, the more the residual stresses. So it's always by all means, try to have the part thickness is quite low. That's why we did not make the whole tube by 3D printing. So it was only that final part where we wanted real transfer of heat faster, which we then printed using 3D printing additive manufacturing. Right, then we also have influence of scanning strategies here. We do have the island strategy. You melt 1 point, say for example, yes, coming up, something like that. So I melt here, then I go wait at that, like that, randomly. Right? That one is on our M2 laser accusing machine. So it seems, yes, it was producing less residual stresses, as we can see here. Okay. But with the experiments which we did with one of our PhD students there, we found that there is this one, the successive chest point here. This one actually, this scanning strategy actually resulted in lesser stresses. That was also another engineering feat which we managed to achieve. Because with this island, that's the best of the art which is being used by our German guys. But with our PhD student there, we managed that this could be another alternative way of having the scanning done. And we also came up with a map now. Say, if you would like to have 100%, almost 100% density, because normally if you build layer by layer, laser accusing, sometimes there will be pores in between, porosity there, it's an issue there. But we found that if one would like to achieve that, you can work with zone 1, where you simply say your scanning speed must be at least 600 degrees Celsius or higher. And your laser power should be at least not 150, 170, okay, or higher. Then you can have your 100% there, almost 100%, 99 to 100%. Then if you are using lesser, lesser values there, say from 500 to 880 there, you find that there's going to be some porosity there. Okay, and all your strength again is going to be compromised. It's going to be, well, less than 300 megapascals compared to the one with for the first region where we are having 300 megapascals in higher. Right. So these, we are happy that we could come up with some fine zones which we could share to the world. That is, this is what we are seeing. This is what we are producing. This is where you can play around if you want, say for example 95% porosity, or if you want 98 porosity, what region can you work in, and what would be the scanning speed, and also what would be the laser power. Now in conclusion, we're saying we came up with a full tune. We managed to achieve a cooling time of 5 seconds, right, leading to reduction in cycle time of about, say, for example, 28%, because the original one, the second one, the conventional, I really wanted a higher cooling time to achieve the 200 degrees Celsius. Then also say we're coming up again with a better cooling system achieved by conventional, achieved by conformal cooling, used by, or rather developed by additive manufacturing means, which would also give us a higher cooling rate of 9.6 compared to the conventional. Well, these are my references, and in my reference there, I also had to highlight my students there. My students, I've also included their work in there for further reading and also citing of their work. Right. With that, may I stop here? And once more, I need to say thank you very much for honoring me. Small as I am, but coming to see me. Thank you.
Thank you so much for the lecture. I think you should know aware. I have to maybe give a minute for questions. Any questions from the floor before I do the vote of thanks? Is there anybody with a desperate question? You can raise your hand. Yes, I do see. Say your name, please, and then the question. You have to shout louder, please.
My question is regarding the cooling tool. I just wanted to know, given the fact that obviously environmentalism and ecocentrism is something that has been introduced into our society and also in the faculty of obviously engineering, I just wanted to know, like regarding the tool, will it be running on renewable energy and all of that, will it be eco-friendly?
Yes, certainly. I'm happy that you're coming up with that. Actually, yes, I'm asking to repeat the question here. Our friend here is saying that this machine, this tool we're coming up with, is it eco-friendly? Isn't it another waste of energy, another waste of resources? In short, that is what he's saying. Right, so the answer there is simply yes. Because with additive manufacturing, we are adding material. The conventional manufacturing, when coming up with product, was machining. So you'll be machining away material and getting it to waste. But with this one here, every little grain is used to be out. So when it comes to, yes, material efficiency, it's quite good. When it comes to material conservation, it's quite good. Yes. Right. And also another thing, maybe you've also seen that our cooling times have been changed as well. Eh? Yeah, exactly. So with that, we can also say now our energy, since our cooling times have been changed, we've also got energy savings there. And also we are saying that we are also producing more. Okay, yeah, thank you.
Okay, so let's give him a big hand again and thank him for the lecture. So thank you very much, Professor Stephen Matope, for successfully delivering, of course, this very insightful inaugural lecture, of course, at the university titled Additive Manufacturing, a Game Changer in Advanced Manufacturing Engineering. And of course, your presentation is really showing the role that additive manufacturing in advanced engineering processes means and the value add that it can give. So today the lecture, as you know, to all our participants, symbolizes the passage of a scholar at any university that you're given to full professorship. And also it tells us about how they've actually reached this level and what they've done as part of their career to be awarded the full rank of professor. So at Stellenbosch University, we really value research for impact, and you can see that from this presentation today, you can see the direct application of engineering and the value that it adds both to the products that you can produce from the theoretical basis, where they're doing theoretical experimental work, to also a practical application where they produce a part that you can use in cars, if I'm correct as well. Yeah? I was just wondering when I was giving the lecture, like, what car will have this part? And how much will it cost? And then I don't know if we can all sort of get to buy it one day. So anyway, so that's also interesting. So I really want to thank you, for explaining so that at least the audience and the public can access this information. So you've shared, of course, the evolution of additive manufacturing from rapid prototyping to producing the final industrial-ready product, which is particularly enlightening, and the potential it offers in minimizing the raw material wastage. I think in some sense, the optimization means that we can also minimize waste, both in time, but also in the materials that we use, from what I understand. So I think that this makes a big impact on the industry. In terms of maximizing not just profit, but also adding to the sustainability value of our planet by addressing some of the sustainable goals and the impact negative, and addressing also the negative impacts on climate change, because depending on the materials we use and how we use them, that can also have a positive impact. So moreover, your exploration of the challenges posed by residual stresses, of course, in additive manufacturing products sheds light on the importance of effective stress management to ensure the production of high-quality components. And we saw that, of course, the collaboration with the German company also helps a lot because we can see the direct application on that as well. I also saw that from this lecture, there's also a potential for interdisciplinary research. So my background is in mathematics, and we work a lot with differential equations. So I was very happy to see the mathematical models and how you go through the whole process to simulation, and using simulations to also at least eliminate parameters that you may not need, but also estimating approximately the measurements that are needed. And also the cooling effect, I think it's amazing how you can actually achieve that cooling in 5 seconds. So I think there's also a lot of potential in terms of further research, I think, that can help to optimize these operations. So your contribution to the field of manufacturing engineering at Stellenbosch University are really commendable. I mean, they're above excellent, and we eagerly anticipate to witness further advances in this dynamic field. You also showed, I think, the students who are involved. How many other students in here? Can you just raise your hands? The 2 PhD students, okay, who are part of this, and then the ones who have joined online. I think that it must be inspiring to see at least what can be achieved. As engineers, your contribution to the quality of life of others, not just the theoretical part, but also the products that can come out of this through commercialization, so when we talk about all these words, we throw them around innovation, but you can see through this work the whole cycle from basic research, fundamental research, to also the products that can come out. So I want to encourage you, and I know that your son also wants to do engineering. You also want to do engineering. I hope it will be mechanical engineering as well, or industrial engineering. I don't know which engineering, but I hope you are inspired to take that further. And I do see also the other students who are with us today are inspired. So thank you again, and I want to then present you with a certificate from us. But before I do that, I should also in advance acknowledge the acting dean, our first female acting dean in the history of the university. Am I correct? Yeah, Professor Leon. So we're really glad that, you give an example as well also to our female students that they can make it. And for me, I take it personally because I know for my daughter also who's doing engineering, I can say there's at least a female dean, and that makes sense. So Professor Connie Scoots as well, really thank you for always inspiring us from the industrial side. I know the industrial engineering department has the best parties. That's how I remember my induction at Stellenbosch University. So I always look forward to that. If I remember my first year, it's industrial or the industrial parties. I know you work hard. I mean, it was not just the parties. So we can see from today the product. So thank you so much for that. And then the head of department, of course, for industrial engineering, the acting head, Professor Joubert, and then, where are you? Oh, yeah, you're right there. Thank you so much as well for joining us. And of course, I'm not allowed to forget our team behind the scenes. I know there will be a vote of thanks, but I should just acknowledge because we host these lectures through the Research, Innovation, and Postgraduate Studies portfolio, and we get a lot of support from the marketing team, the corporate team, and the registrar's team. And I know they will be mentioned by name according to the program that has been given. So I just want to acknowledge their support. And I know Jonathan and the others who are running around somewhere. So thank you to the faculty. So can I present the certificate and then ask the audience to clap once it receives it, please. Look happy. At least we're at the end of the lecture. Thank you. Thank you so much.
Colleagues, friends, family, there are a lot of things that happens behind the scenes, and it's all important to say the thank yous. First of all, I again want to say, Professor Stephen Matope, thank you for your presentation. I could see, as you put layer of additive manufacturing to us, as you presented that, I could see you cool down and you have very little residual stress at this moment. In terms of the rectorate, our Deputy Vice Chancellor of Research, Innovation and Postgraduate Studies, Professor Sibiti Sumoyo, thank you very much for officiating the proceedings and doing the handover to Professor Matope. Then behind the scenes, a number of people have been involved that we want to thank. Corporate communication, especially Amira Brown and Cindy Arendse for their arrangements for tonight. Then the coordinator for publications, specifically Jonathan Dale Blankenberg, who within the Center for Governance Function Support, thank you to them as well. Then to the Dean's Office, so this venue, Ulrich and Clint, for all their preparations to get the Rights Hall ready for tonight. Also for Murali, Stephen said specifically I must thank Murali as well. She's always behind the scenes, making sure that everything runs smoothly. Justin Albert for the recording, thank you very much for that, and the live streaming of this lecture. And then as a last thank you also to everybody that the family and the extended family of Stephen Matope that actually made this possible for him. Over all these many years, I won't say how many, he's been on a journey to here, and I want to say thank you to everybody that's been part of that journey, close family and further. Okay, and then what we want to ask you, we're going to have a function outside that we all, ask all of you to please come and join us for that. If you can please rise for the procession to leave, and then you can join us outside for refreshments. Thank you.